Okay, so students, we start with video lecture 9. Now, this lecture is not what I designed for, but I thought because of the discussions and the many questions that are being raised, I thought of taking one class and clarifying some of these questions. One question is that I will address in this video lecture is there a difference in structures between the two end members? That's point number one. Then we have another question regarding the choice of components. Somebody talked about the rhodonite part of it, Mn2Si2O6, Fe2Si2O6, Ca2Si2O6. So when we say Ci2O6 to Ca2Si2O6, do we mean that there is rhodonite? And then there was the third question, which essentially was, I take a clinopyroxene, a garnet, a plagioclase and quartz and consider the system as NCF mesh with the H, although the phases, garnet, clinopyroxene, plagioclase, quartz, they don't have any hydroxyl molecules. So, but how does H2O come in and how do we find it? So these are the three questions. So I would like to address these questions. But before I do that, I think I need to talk a little bit about mineralogy. You see, thermodynamics that we talk about, chemical thermodynamics, is about macroscopic thermodynamic parameters. They don't go into the molecular level. But the macroscopic properties are a function of the microscopics, the microstructure of the minerals. They are not separate. They are not separate entities. The microstructural entities, their entropy, their enthalpy, etc., contribute to the total free energy of a particular mineral at a particular pressure temperature. Only thing when we do thermodynamics, we do not talk about the microstructural part of it, but there is a direct transition and you can actually calculate what they will be. But that is not a part of this course. If I go on teaching this, then it would be teaching thermodynamics, but this is a course on metamorphic phase equilibria. So I think what I will try to do is, this lecture, I will talk a little bit about mineralogy so that your mind gets clear about certain things. And the other thing is, remember the questions that I will address. One question is of having Mn2Si2O6, Fe2Si2O6, Ca2Si2O6. The second point is whether they should have different thermodynamic properties. Yes, they should have different thermodynamic properties. And whether about NCF MASH business that we are talking about, there was some debate in the class. So before going into that, let me first give you a little bit of idea of the different elements. And the first thing that you should know about it, and this is what Linus Pauling told us about what is something called radius ratio and coordination numbers. Now let me just write down some of if you analyze elements all over the earth, in different parts of the earth, there are certain elements which occur, all elements of the periodic table occur in every mineral. But they occur in varying proportions, like some are in the proportion of weight percent, some are present in the proportion of parts per million. That means how many parts per 10 to the power 6, and then parts per billion, 1 in 10 to the power 9. So all elements are there in all elements, in all minerals and all rocks, but the proportion varies. So right now I will list some of the more major elements that occur in the Earth's crust and Earth as a whole. And then I will show you the abundance of these elements as you see them between the Earth's crust and the core, and then we will talk about radius ratio, etc. So the elements that dominate are silicon, aluminium, titanium, ferric iron. Remember, this is 4 plus, this is 3 plus, this is 4 plus, then Fe2 plus, Mn2 plus, Mg2 plus, Ca2 plus, Na plus, K plus, and then we have oxygen minus. That is the important thing, the oxygen minus. Now if I tell you about the ionic radius, which is in angstrom units, I will just write it down and you better remember them. 0.42 angstroms silicon, aluminium 0.51 angstroms, titanium 0.68 angstroms, ferric iron 0.64 angstroms, ferrous 0.74 angstroms, Mn is 0.80 angstroms, magnesium 0.66 angstroms, calcium 0.99 angstroms, sodium 0.97 and 1.33 angstroms, and oxygen is 1.40 angstroms. These are all positively charged and they are linked to oxygen. This is the range of ionic radius. As we see, silicon is the smallest ionic radius and oxygen is 1.40 angstroms. So this is the smallest and this is the largest. This is about the ionic radius. Now I should tell you, maybe you know, that there are different types of ionic radius, like ionic radius for an ionic state or covalent, or there are different ways they occur, but we take a very generalized value of these elements. So it depends also on the coordination number, but we don't go into, or the charge, etc., and we don't go into those complications at the moment. It's not necessary. Now, these are the elements that occur in weight percent in the Earth as well as in the Earth's crust. So now, what I will do is, I will draw two circles. This is for the Earth, and this is for the crust. And I will only give you the abundance of those elements which occur in high amounts. And these values are in weight percent. Remember what I am saying, it's in weight percent. All these values that I am giving you is in weight percent. Now, just give me some time to draw it. It takes a little time. Now this is 29.76 and this is oxygen. 29.76 weight percent oxygen if you take the whole Earth. This is 31.9% and this is for iron, Fe2 plus. And silicon, this is 16.1% and this is silicon, and this is 15.4%, and this is magnesium. This is aluminium, 1.6%, and here you have different other elements. This is 1.8% is nickel. So this is that of Earth. So the dominant elements here in weight percent is 29.76 weight percent of oxygen if you take the whole Earth. It is less than 31.9. Iron is the most dominant element if you take the Earth. Then you have oxygen, 29.76 weight percent. Then you have silicon, which is 16.1%, and magnesium, which is 15.4%. These are all weight percentages. The rest of the elements that occur in this table, they are much less. Among that, nickel, which is mildly restricted to the core of the Earth, and that's 1.8%, and aluminium, which is largely restricted in the crust of the Earth, and also in the uppermost mantle and the mantle, is 1.6 weight percent. Now this figure completely changes if we take the Earth's crust. So let's see how it looks like. So this is the abundance of these elements if you take the Earth and the crust. You can see here there are major differences. While oxygen in the crust, oxygen is 46.4, the value comes down to 29.6, a drop of 15 weight percent. And the very high increase is that of iron, which is 5.63% in the Earth's crust. This goes up to 31.9% if you take the whole Earth into consideration. Also, magnesium, which is 15.4% in the Earth, is down to 2.33% in the Earth's crust. These are the other elements. I have not listed all. In fact, if you can just write element abundances in the Earth, element abundances in the crust of the internet, you get the perfect figures. Now, so therefore, all these elements don't occur in the same abundance in the crust. They vary. The important, if we ignore the Earth at the moment and we take the crust, you can see oxygen is 46.4, silicon is 28.2, and aluminium is 8.2. Now if you add this, it's 0.8 to 82.8 weight percent of the Earth's crust. Weight percent of the Earth's crust is composed of oxygen, silicon and aluminium, followed by iron and magnesium. So if you can imagine the crust, then essentially about 82% of it is composed of oxygen, 46.4. The ionic radius of oxygen from here, the ionic radius of oxygen is 1.40 angstroms. Silicon is 0.42 angstroms. And if I take aluminium, it is 0.51 angstroms. Now, when I take the volume, it is equal to 4 by 3 pi r cubed. That is volume. Right? So if I want to convert this weight percent into volume, you will see, you can imagine, this R is cubed. Right? Cubed. This high value is cubed. And these two low value are also cubed. So you can imagine that if you take the volume percent of the element, you can do it yourself. These are very simple calculations. So if you take the volume percentage of oxygen, silicon and aluminium in the crust, they would consist of more than 94%. 95% of the Earth's crust is by volume oxygen and silicon, and out of which oxygen is way dominant, about 82% by volume. So if you're looking at the crust of the Earth, you're essentially looking of what will you look at? You will look at half of it is almost silicon, and each silicon atom is very large. The next competing one close to potassium, you can't, it's not even, comes here as a very small bar. And if you take the Earth's crust, it's very, very small weight percent. So, you have oxygen. So, if you look at the crust, then oxygen is the most dominant, half of it, and has a very large volume. So, essentially what you're looking at, if you look at the crust of the Earth, you have oxygen and you have silicon and you have aluminium, out of which oxygen is dominant. Where do the rest of the cations are? Obviously, they are in the interstices of this oxygen and silicon atoms. They are at the interstices. So essentially, all the cations that you see, other than oxygen, silicon and aluminium, they are in a whole form of oxygen, a whole form of oxygen and silicon and aluminium. They are in the interstices to form small minerals that are electrically neutral. Now we come then how will you accommodate all these cations within oxygen structure? We come to a very important question. How is then in a mineral oxygen, which is very large and hugely abundant, and how do the cations go into the crystal side? I will give you a few examples. Okay, I will erase this. I think we are done with this. Two things come here. Two things become important. With so much oxygen around, and the cations only occupying small positions within this oxygen, two things come in. The number of oxygens that surround the cation, the number of oxygen that surround the cation, or technically there is a name for it, the nearest neighbor oxygen. how many oxygen atoms surrounds a particular cation, which means the cation also has to have bonds so that it can link up with the oxygen atoms. So what happens here is two things become important. The number of the nearest neighbor oxygen around the cation and how the oxygens are packed. How the oxygens are packed. Right? These are the two things that dominantly matter. Now the number of oxygens or the anions in general surrounding a cation is called the coordination number. Is called the coordination number. Have you understood? The number of the nearest neighbor oxygen that surround the cation, or in this case oxygen and the cation, generally anion and say for example if you have taken a sulfide mineral, there is no oxygen there and sulfur would have been the anion. So in a silicate mineral, normally silicate minerals are very dominant. So it is, you will have silicon oxygen bonds, iron oxygen bonds, magnesium oxygen bonds, aluminium oxygen bonds. So what happens is the number of anion oxygens here surrounding a cation becomes very important. How? Let me show you. Say for example, let us take a square. Let us take a square. That means, let's say you have seen table tennis balls. So, table tennis balls. So you take a table and put 2 table tennis balls, 4 table tennis balls and make it on a plane. Have you understood? You take 4 table tennis blocks and place it in a plane. The table tennis blocks are spheres, so they are touching each other, just touching. Ionic bonding. They are touching each other. They are not compressing. Assume the oxygen atoms as non-compressible or incompressible cations. And they are lying on a particular plane. So we can say, okay, we have our oxygen atoms. And these are only 1/4 of it. The other ones are like this, as you can imagine. So these are the oxygen atom, and the centers of the oxygen atoms are here. So the centers of the oxygen atoms, oxygen ions, corners of the squares. And so we name this distance as RA, radius of the anion. Right? Similarly, this is also RA here, and this is also RA, and this is also RA. So all of them are RA. So each of the side here is 2RA. Right? And now, in this space, we put in a cation. You see, in this space, we put in a cation. And the radius of the cation, say, is called RC. So you have RA and RC. Many of you know it. This is the radius of the anion and this is the radius of the cation. Now, if this is RA, then what is RC in terms of RA? So what you do is, you draw a diagonal through the center of it. Remember, this is RA, this is RA, and this distance here is 2RC. Because it's the diameter, it passes through the diameter of the material, of the cation lodged inside. So how can I find this out? So you see the long diagonal, therefore is equal to 2, what is the length? 2RA squared plus 2RA squared. Right? The long diagonal. So this is equal to 4Ra squared plus 4Ra squared. So this is long diagonal square. So the diagonal will be D is equal to will be 2 root 2 Ra. Have you understood? D is equal to 2Ra whole squared plus 2Ra whole squared, 4Ra squared plus 4Ra squared. So essentially it is 8Ra squared. And so if you take out the roots, then you have 2 into 2Ra. If you do the square, 4 into 2, 8. So this is 2Ra, diagonal. But this 2R2Ra is equal to, this diagonal is also equal to 2Ra plus 2RC. Because the diameter is 2RC. So we can cancel off 2, 2 and 2. And we can write RC is equal to RA into root 2 minus 1. Now root 2 is equal to 1.414. So this value is equal to 0.414. Okay? That means for, and how many, so this cation is surrounded by 4 oxygen atoms. So it has a coordination number of 4 coordination, and the RC by RA value is 0.414. RC by RA value is 0.414, where the coordination number is 4. Right? Now, if I take my Ra anion is equal to 1.40, then RC for oxygen will be equal to 0.414 into 1.40 angstroms. That means that value will be 0.58 angstroms. I think I've got this right. That if you have RC by RA is 1.414 and you multiply it by 1.40, then what you get is 0.58 angstroms. So if your coordinating anion is oxygen with a radius 1.40 and it is arranged in the form of a planar square, then the cation that can be lodged here, which smugly fits in without compressing anything, ionic bonding, it should have a value of 0.58 angstroms. If the radius of the cation is smaller, the whole structure collapses. If the ionic radius is larger, then it cannot be admitted into this arrangement. So you can see here, none of these elements really perfectly fit into this value. Have you understood? Do not perfectly fit into this value. But there is another problem. This is not the only way where 4 oxygen atoms can be arranged. You can also arrange the 4 oxygen atoms as an equilateral triangle at the base and put a table tennis ball right at the top. So it's a tetrahedron. So it becomes a tetrahedron where you have 3 balls in an equilateral triangle and one above, and there will be a small space in between that. And that is where a cation will go in. Now you see, for the cation that goes into the center of that, is also surrounded by 4 oxygen atoms. So, although the coordination number has remained the same for this square and also for the tetrahedron, the packing of the oxygen atoms is different. Because of that difference, the radius of the cation for a tetrahedron arrangement would be different. And I will not derive it on the board. The value will be RC by RA value will be 0.225. Now, I leave it to you to find out the derivation from wherever you want. I want you to do the derivation from wherever you can. There are 2 or 3 ways to do it. You can do any one of it. But what I am trying to say important here is that for 4-fold coordination, the range is therefore not only 0.414, but it can also have a range from 0.225 to 0.414. That will be the range of the radius ratio. Range of the radius ratio for a 4-fold coordination for different packing geometries. Now you can see, I will try and get you the value. If you take oxygen 1.40 as the coordinating anion, then the ionic radius range will be between 0.32 to 0.58. Now you can say these 3 elements will have 4-fold coordination. This 3 will have 4-fold coordination. But these are much, much bigger to be accommodated in a silicate structure under 4-fold coordination. You cannot do it. So that is very important, that the silicon-oxygen bond, there is another complication to it. I will tell that to you. You see here, so once more, just before I go into the next stop, the important point here is the radius ratio for 4-fold coordination has a range. The range here is because of the different type of packing that can be employed with the same number of oxygen atoms, and for which the radius ratio should vary from 0.225 to 0.414. And therefore, 0.32 to 0.48 angstroms cations with this ionic size can be admitted into the crystal structure. But there is an assumption, a very fundamental assumption. What assumption? We have said the spheres are incompressible, which is complete ionic bonding. But this does not happen. Why? Let's say, if I take a silicon ion and an oxygen ion, and I take this distance, then this distance is 0.42 angstroms, and this distance is 1.40 angstroms. So, the silicon-oxygen bond length would be equal to 1.82 angstroms. The silicon-oxygen bond length, if they were ionically bonded, would be 1.82 angstroms. But what happens? The silicon-oxygen bond length has been experimentally determined in many crystal systems, silicate crystal systems. And it has been found that the silicon-oxygen bond length is very close to 1.62 angstroms. What does this mean? That the actual measured silicon-oxygen bond length in naturally occurring and synthetic minerals, experimentally determined, is smaller than what Pauling suggested. It's 1.82 angstrom if you take ionic bonding, which means to say that silicon-oxygen bond is not an ionic bond. If you know it correctly, you know, I don't know whether you know it, electronegativity scales. If you do, there is a graph which you studied in school, I think, highest classes, 11 and 12, that you have what is called electronegativity scale on the x-axis, and on the y-axis you have what is called ionicity of covalent bond or covalency of ionic bond. If you do that, you will see the difference in the electronegativity between silicon and oxygen puts it at 60% covalent and 40% ionic. Silicon-oxygen bond is not an ionic bond. It is a 60% covalent, 40% ionic bond. So that means these theoretical values of 1.40 goes out of the windows in natural minerals. Have you understood? That's the important thing. So that is why this ionic radius always has a range. This is after extensive theoretical and experimental studies. This has been suggested, assuming dominantly ionic bonding. But when you have most minerals have covalent bonding, that is why the crust of the earth is a very bad conductor. You know, if you have covalent, strong covalency, then such material have certain properties, covalent properties. What is it? High melting temperature. This you studied in school. High melting temperature. Crust rocks with high melting temperature. Say, for example, they are very good insulator or bad electrode, very low electrical conductivity. It's true. It is insoluble in water. It is true. So these are some of the properties of the crust, which essentially comes because of the silicon-oxygen bond is strongly covalent, more covalency than ionicity, because of the electronegativity difference. This also you can find out from the internet. There are very famous graphs. This was also suggested by Linus Pauling. So what I'm trying to say here, we have seen here that if you arrange for an ion, 4 oxygens, and try to put in a cation in the vacant spaces, then if you have 4 of them, 4 oxygen atoms, either in the form of a planar square or in the form of a tetrahedron, which I asked you to find out from the internet how it is derived, the value the radius of the cation should be between 0.32 and 0.58 angstroms. And if these elements are there, then you see they should be part of tetrahedral or 4-fold coordination. Right? 4-fold coordination. Now, let's do one thing. Let's change the coordination number. Let's say we take a cube. Let's say we take a cube. We take a cube. And you have now 1, 2, 3, 4, 5, 6, 7, 8. 8 oxygen atoms. So this is a case of 8 coordination number. It is a question of 8 coordination number. So you have oxygens with the centers of the spherical incompressible oxygen coinciding with the 8 corners of the vertices of the cube, and inside there will be a small cation, and the length of this, all the length of this will be 2Ra, because half and half 2Ra will be equal to 2Ra. What will that be? So this is the diagonal of a face, right? The diagonal of a face, and then you will have a diagonal which is here. So this is the short diagonal and this is the long diagonal, and here you will have a cation at the center whose diameter is 2Rc, whose diameter will be 2Rc. And, right? So now we find out what is the short diagonal distance. We found out just before. 2 root 2 Ra. Just like a square. 2 root 2 Ra. Right? So this is 2 root 2 Ra. And this is 2 Ra. So now you look at this triangle, this face, this is 90 degree. So now we can find out long diagonal square is equal to short diagonal square plus 2Ra whole square. Yes or no? And so short diagonal square would be 8Ra square, and 2Ra square, this should be 4Ra squared, and therefore if you take it out, then it should be 12Ra squared. This would be then 4Ra squared into 3. So 3 root 2 Ra will be. So the long diagonal will be equal to 3 root 2 Ra. Long diagonal will be 3 root 2 Ra. But long diagonal also is equal to, there will be 2Ra plus 2Rc is equal to 3 root 2 Ra, which is this value. So we have now 2Rc will be equal to 2 Ra 3 root 2 minus 2 3 root 2 minus 2, and this should be it. And therefore you will have Rc by Ra is equal to 3 root 2 minus 2 divided by 2. Have you understood? So this value will be equal to, if I divide it by 2, then this should be 3 by root 2, minus 1. Where did I make a mistake? Anyway, you can check it out. This value will be 0.732. This value will be 0.732. I think I made a mistake somewhere. So you have the long diagonal 2Ra squared. So it's 8Ra squared. Ra squared plus 4Ra squared, 12Ra squared. So LD will be, oh, that's the problem. Sorry. to root 3 Ra. So if you do this, Ra plus Rc, so Rc will be equal to root 3 Ra minus Ra. So root 3 is 1.732, is 1.732 Ra. That means Rc by Ra is equal to 0.732. And this, if anion is oxygen, Rc by Ra 732 will be equal to 1.02 angstroms. Rc (1.02 angstroms). That is 0.732 into 1.40 for oxygen. It should be 1.02 angstroms. So 1.02 angstroms, you can see, is very close to calcium and sodium. So you see, calcium and sodium are very good candidates to go into an 8-fold coordination. So you see, the number of coordinating oxygen atoms is dictating number of coordinating oxygen atoms and the packing arrangement of the oxygen atoms and the covalency of the silicic oxygen atom and the covalency of the bonds are dictating what will be the radius ratio and coordination number ratio. Okay, so from this a small table is calculated, which is famously taught to you in geochemistry class, or I don't know where you taught, but I'm sure you have been taught. And so you have the table where you have radius ratio, ionic radius if O2 minus is this thing, and coordination number. So you have this table. So the radius ratio values 0.155, 0.155 to 0.225, 0.225 to 0.432 or 414, 0.414 to 0.732, 0.732 to 1.0 and 1.0. These are the ratios that are possible, and for this, the coordination number is 2, 3, 4, 6, 8, and 12. These are the coordination number. And ionic radius ratio values is less than 0.22 angstroms, 0.22 to 0.32 angstroms, 0.32 to 0.58 angstroms, 0.58 to 1.02 angstroms, 1.02 to 1.40 angstroms, and this is 1.40 angstroms. So these are the ionic radius if the coordinating anion is oxygen. That means this value is multiplied into 1.4. All values are multiplied into 1.4. Now you can see here the interesting point that I would like to say is these elements here, these elements go into the 4-fold site. Do you see that? And these set of elements here go into the 6-fold site. And these set of elements here could go here or they could go here. And all those here is this one. This can either go to 12 crystallographic sites. So that is what happens here. So all these cations, they are not arranged or replaceable at the same position of a crystal structure. It is not. It doesn't happen that way. So these cations occur at specific places within a crystallographic mirror. Now coming back to your first question. If this is the case, then say for example you have CaSiO3, MgSiO3 and FeSiO3. The first question. Now you see calcium here has 0.99 angstroms. Calcium. Magnesium is 0.66 angstroms and iron here is 0.74 angstroms. So you can see all these components, thermodynamic components, CaSiO3, MgSiO3, FeSiO3, these have different structures. Well, the silicon oxygen is the same, but you have different cations lodged. Different cations lodged in 6-fold coordination. 6 or calcium could go into 8-fold coordination. So you can see what happens, whereas silicon is always 4-fold. Silicon is always 4-fold, magnesium is 6-fold, iron is 6-fold, but calcium could be either 6-fold or 8-fold coordination. Calcium could be either 6-fold or 8-fold coordination. Magnesium is 6-fold coordination, iron is 6-fold coordination, and they have different ionic radius. So obviously the structure of the 3 components that make up your orthopyroxene or whatever that element is, these end-member data are really going to be different. The free energy, the enthalpy, the entropy, the volume. You can imagine already. CaSiO3, someone asked about wollastonite. Or say for example, I think someone asked MnSiO3, right? Yeah, MnSiO3. Now you see Mn has an ionic radius of 0.80. Now you see here, if you have manganese, it's close to, you see manganese has a structure which is close to FeSiO3. But that structure is very different from that of MgSiO3, which is enstatite. And it has a completely different structure from wollastonite. Do you understand? So these variations in crystal structure is because of the accommodation of the different cations as controlled by the symmetry elements. They will have different microscopic properties and therefore they will have different macroscopic thermodynamic properties. Okay, I think I will stop here. It's a 1-hour lecture already. This will trickle down to a next lecture. We will see how it goes, but this is not what was I intended. Anyway, I hope this has helped you a little bit in understanding the crystal structures and how it travels to. I can't derive the microscopic to macroscopic quantity. This is not a thermodynamics class. You would require a lot of theory for it, so I don't go into it. But I think overall you understand. And more you will understand as I go on. More you will understand how does the macroscopic property tells you which one will form a solid solution, which not a mixed solution, whatever it is, we will soon find out. And therefore also just in continuation of that, If you have an orthopyroxene MgFe SiO3, you can imagine therefore the crystal structure where iron is, magnesium is not there. It is not favored because iron requires a higher location to be there, a higher space, a larger space to be accommodated than magnesium. So even here, the two end members don't have identical end member properties. They don't have. Neither do they have same end member thermodynamic properties. We will continue in the next lecture.